Thanks for coming, everybody. A lot of you have probably already seen me present the roadmap, so this won't be just the standard presentation. It'll be a little bit quick and fun, just to help get you guys some context for why we're here. In case anybody doesn't know who I am, Mark Hamalaien. I've worked in biotech for 20 years now, mostly in technology development for making things go faster. Nathan Cheng, my co-founder in the back. Couldn't be doing this without him. He's amazing. Also does a lot of projects. Let's get to the point here. Put up your hand. Who here thinks involuntary death is a good thing? Anybody?
Wrong crowd.
Oh, wow, okay. So we think life is good and death is bad, and that the ultimate goal should be to extend lifespan indefinitely, like just by induction. But how is the harder part. We also think this is an emergency, and that in general, as a society, we're not treating it like one. Nobody here put up their hand saying they want to die involuntarily. But this is the situation we're in right now. It's pretty dire. And the state of longevity is that we have 0 interventions approved for aging. I've been in this field for, like I said, 20 years, and we've gone from 0 to 0. That's not a great trajectory if you draw a graph. We have maybe 1 for mice if you use the sort of 900-day rule, which people have proposed more recently, which is rapamycin. There's an interesting thread here. I don't know if there's a QR code, and this is all publicly available on our website. This is debatable. There are some germline genetic modifications that do work, but we don't have gene delivery to actually make that happen. So I don't know if you would count that, because it's not going to help any of you guys that are already alive. And then, why are we here today? So you guys are mostly experts in this field. We're not here to educate you. You guys know, we all know probably a lot about topics, more than most people. But we're often specialized. And I think we should all be very open to constructive criticism. And as Nathan put it, we don't be polite, don't feel pressure to just agree with people. We want this to be an idea lab. I don't know if anyone of you guys follow Tim Urban. He wrote a pretty fun short read book, but the idea is that you should be able to disagree and not offend each other. Don't hold ideas, don't identify with ideas. Allow ideas to be open to change. And so I want everybody here today to challenge each other. When somebody says something and you think, I don't know if that's really justifiable, actually confront them about it, and they can benefit from that.
I don't think that pessimism is justifiable.
We'll talk about that at beer later. Just an example, idea lab discussion. This is a fun diagram from the book. I think the echo chamber in the broader world is it's not about quality, it's number, health span is the goal. Death gives life meaning. I get bored. I don't think people are actually thinking when they say this. They're just repeating what they've heard from other people. That's an echo chamber. We're here to discuss ideas. Now, what ideas? That I mentioned indefinite lifespan as being the goal. So how do you achieve indefinite lifespan? And this is something that I want constructive feedback on, because we did a survey of 400 people, and we've interviewed over 60, maybe closer to 80 experts in the field right now. And the only plausible paths that we've identified are what I would call biostasis, replacement, and advanced bioengineering. And I'll quickly cover those. So you can break these into categories. Advanced bioengineering is where you actually try to understand biology, model it, and modify it. You can think of pharmacology, I would say, as primitive bioengineering, where you're just sort of using drugs to modulate the things that you already have in your body. But we already know that there's not some magical latent ability to live forever, and you just need to give somebody a drug and then they won't age anymore. I mean, if somebody disagrees with me on that one, let's talk it out. But I haven't heard a plausible case for that being possible. We're going to have to modify our biology if we don't want to age, and that's difficult. But you have to understand aging to do that. And then there's approaches where you can bypass understanding. You don't have to understand aging to just replace old parts with young parts. Allison mentioned that one. And biostasis, of course, is just putting people on pause until we can solve the problem. Yeah, like I said, why not pharma? This is my position. Challenge me. If you disagree, I just view aging as a problem that drugs are not going to solve. But if you disagree with me, I'm happy to debate. I'm not going to get into the details. And of course, one of the sessions is AI or tools. And yeah, Shruti, I don't know what you think of that one, but but yeah, I just think of AI as a tool, right? We're always developing new tools, which just allows us to do biotech faster, better, more reproducible. Same like automation, right? So you should either be using or developing the latest tools. If you're doing things the way people did things 20 years ago, there's a good chance that when you look back in history, what you did didn't actually matter. So use the latest tools. There's also a bunch of bottlenecks, and I'll just quickly go over to this. Why are we not making progress fast enough? Why is this still an emergency that we should be feeling a lot of urgency about? And we did a survey, and the top 3 things that people complained about were lack of public data, lack of biomarkers, like how do you even know if what you're doing is affecting aging, and then lack of funding. I think it's interesting that funding wasn't at the top, but partly I think is that if we had biomarkers and models, funding would actually probably flow more easily, right? So it's hard to convince somebody to fund your aging plan if you don't even know how you would measure whether it's working or not. So maybe that's what's going on there, but we can psychoanalyze each other later. And I'll just mention a few notes on those particular bottlenecks that people highlighted. So actually, wait, before that, hopefully nobody saw the text. Everybody in your head, you've probably heard about AlphaFold, right? It cost $20 million to train the model. How much do you think the cost of generating the training data was? Just come up with a number in your head. How much did it cost to generate the training data? Come up with a number in your head. Now I'll tell you the actual number. Most people guess around $50 million or less. It was $20 billion. Yeah. And that's to solve one narrow problem in biology, right? So I think a lot of people in the machine learning and AI communities are moving into biology right now, but they don't understand how expensive it is to generate data. And that is like a very serious problem. And right now, the only way to generate the data that we need is with government funding. If we could lower the cost of data generation or come up with a business model where people pay for it themselves, there's a lot of strategies one might think, but data generation is a huge bottleneck that I think the machine learning people are going to realize pretty quickly that they just don't have the data to do anything interesting. Chan Zuckerberg initiative also puts a lot of money into data generation. I think that's awesome. I would wish more rich people did that. And then aging biomarkers. I'm not going to cover this because we have a big session tomorrow, but if you're really into this stuff, you should probably check out this project. I think it was actually like sort of had its genesis at a Foresight event, right, Alison? Ish, yeah, it was, yeah. So, but these are awesome people. You should go to that conference if you want to dig deeper, and we'll also cover it tomorrow. And then funding was the third thing. And I just want to, in our survey, we asked people sort of like, what was the potential impact of a sort of research direction? And then we compared that to how much money goes into those directions. And currently there's an inverse relationship between how much impact we think a research direction could have and how much money it gets. It's completely opposite, actually. And so, for instance, you can see that pharma gets, as actually you'd have to make this thing like 2.5 times taller to see that one, but then cryo and replacement actually don't actually even get a pixel. I just put it there just so you know where it would be. just saying. And those are the ones that, you know, could actually solve the problem. It's not as bad in bioengineering, although I would say most of bioengineering is sort of narrowly targeting diseases and using technologies that we know wouldn't be relevant for aging. bioengineering is sort of the default mode. It's kind of like what people continue to do when they haven't thought about alternatives. And the interesting thing is, I don't think it's actually the researchers or the scientists that are the problem, because we've polled, this is cumulative data from multiple conferences where I poll people that are scientists and engineers, how they would distribute the funds. And they distribute the funds in the way that matches with what the potential impact is. It's the funders that are actually the problem. And so we should just be saying over and over again to these people, we just have to keep saying it, like, no, like, this is important, this is what should be funded, you're wrong. And if everybody says it, then maybe they'll listen. Yeah, so people want to fund the stuff that could work. Look at this. That's what they want. That's the status. Replace old parts with young. We're going to have sessions on this, but also in our survey that we did, replacement was the only one that sort of people thought could give you escape velocity within 25 years. Nobody thought that any of the other approaches to gene therapies were the next best, and cellular reprogramming was the next one after that. They're kind of related though, because you probably need gene therapy to do cellular reprogramming. So if you want to look at what people in the field think would have the biggest impact, it's replacement, followed by better gene delivery and editing, followed by cellular reprogramming, probably, yeah. And the other stuff is pretty low impact after that. Interestingly, I think this is catching on. This might be the next big wave, because Impetus Grants just said that they are interested all of a sudden. They used to not be interested, and now they are. Maybe somebody read this book. I don't know. I keep leaving copies of it in like hotel lobbies and airports and things. Maybe it worked. So replacement, for anybody who doesn't know, you can replace old parts with young. By definition, they are now young. There's obviously difficulties there, but like you could imagine doing like a kidney, but if you're gonna do an organ, why not just do the whole body? And then there's the brain, which you can do progressively. I don't have time to get into the details, but Jean Hebert gave a talk, Foresight talk, and has a book. You should check them out. There's a lot of hard technical problems here, and these are what we want to dive into at this workshop. Like, tell us why this isn't going to work. Challenge us. Jean Hebert is here. Tell him why this isn't going to work. He probably has good answers though, so he's thought about this a little bit. And yeah, like I said, Impetus is getting into this. Age 1 is talking about this. ARPA-H is talking about this. So yeah, it seems trendy. That's really cool. The amount of funding still has not been deployed, but the interest seems to be growing. And there's a long list of startups, most of them stealth. Except for Omri. He's willing to stick his neck out and just fucking say it. Am I allowed to swear? And yeah, and it's like an engineering problem potentially. Like we've made budgets. There will be a more detailed version of this coming out soon. The detailed cryo one is actually going to be out this weekend, so you'll hear more about that later today. Biostasis, I don't know, is Laura here yet? I don't know. So biology is really complicated. So this stuff like goes terribly wrong over time. It drifts from equilibrium. It's accumulating damage and deviations, and we still don't understand most of it. So yeah, I don't know. I think having a backup plan is important. There are technical challenges, and you'll hear about that from people in the lightning talk session. But is cryo having a renaissance? It seems like it's interesting. Like there was a big conference last week. There's a lot of new companies, and again, unlike it's like something where like you can test all of, like we have a good set of ideas that we could test that are plausibly could solve the problem, and they just haven't been, like people just haven't done it because they don't have funding. But if they did, we could, for a rounding error on what we spend in pharma, we could test all of the ideas. And then bioengineering, this is the default mode where you try to understand and gain full engineering control of biology. This is extremely hard. I think Michael Antonov here, you started off with this idea of doing full cell simulation, quickly realized, holy shit, this is hard. I think it's like, the nice thing here is that intermediate goals along the way actually get you a lot, right? So they buy time. And so it's kind of an accelerating positive feedback loop potentially, where you're like gaining more and more capability, and there's more excitement, and you start curing diseases, and then you start increasing aging, but it's very hard and very expensive. And so while it's, I would say, the most active of the three areas, it's also the hardest. And yeah, I'm going to skip over this because we don't have time. I just want to highlight a few crazy ideas here. And this is to give you guys some inspiration for the workshops, because the idea with the workshops today is to come up with cool ideas for projects. And so here's an example. We don't know what all of aging is. So why don't you just take tiny little cubes or spheres of cells from every part of the body, extracellular, everything, just like random sample of little bits of all of the body that are just the right size that you can put them in an X-ray laser and get atomic resolution images, and then just see if what you get, if it matches any of your understanding of biology and of aging, right? Like it's just pure empirical. And people have done entire single virus particles atomic resolution at the Stanford Linear Accelerator. You can make a bigger laser, do bigger things. We need better gene delivery. Yeah, I just like to say, like, current gene delivery is about as good as throwing a bucket of paint in the air and hoping every grain of sand on the beach gets the same amount of paint. We need a lot better technology for gene delivery, and it is getting better. There's a lot of stuff going on here. I have ideas for this, but I won't bias you guys. You guys come up with your own new ideas, and we can talk about mine later. Modeling, we have things like AlphaFold. We have generative algorithms to design proteins now. These are solving sort of narrow problems, but like the goal of like full cell simulation, that's still pretty far away. That would be like the holy grail though, because then you can do dry lab experiments and you just add more GPUs if you want to do more experiments. But we're still a little ways from that. Probably talk to Michael and other people here if you're interested in that stuff. They can tell you why it's really hard, but they can probably also tell you what the potential paths are. And you can't make time and cost estimates for bioengineering because it's full of unknown unknowns, because we haven't fully characterized aging, so we don't even know what all the problems are. Okay, so where are we? The current state of things is that this is a tiny field. It's very niche. It is growing, but it's still very niche. But I would say we really need to like get people to feel more of a sense of urgency here. That like I'm always just like, oh, this is too early. Like, yeah. And so waiting another 5 years, how does that improve your chances of survival? I don't understand the logic. So yeah, don't wait. Like if you want to not die, like, you know, it's like planting a tree. You should have started 20 years ago, but it's at least start now. Don't wait for another 5 years. And just to say about the LBF, I didn't really explain what the LBF is, but we try to recruit top talent from other fields and get them to work on this problem. So if you know anybody who doesn't work on aging and is really smart and doesn't want to die, but is doing like, you know, optimizing click-through rates or, I don't know, selling hedge funds bonds or something, I don't know, like send them to us, we'll radicalize them and get them on a better path. That's our job. Yeah, send them, we'll join our cult. Yeah, so let's break the limits to human lifespan. That is my message. So lots of opportunities. The LBF has a roadmap, a podcast. We're trying to raise a fund. LPs right now don't seem very interested for whatever reason. It's like ROI is too long or something, but we're still gonna hack at that. So that is it. Now we can start the lightning talks. We're probably slightly behind schedule, but that's okay.